Chapter 2, Stress and Strain, homework. Homework 2.1. A plastic wire is pulled by a tensile force of 4 Newton and its length increases by 1%. Its length increases by 1%. That is essentially our so-called relative deformation or strain is 1% or 0.01. So if the plastic material has an elastic modulus, or we call Young's modulus of 4 gigapascal, if we assume that the deformation is well within elastic limit, when we say well within elastic limit, that typically means we can use the so-called Hooke's law, linking engineering stress and engineering strain. And we want you to calculate the average normal stress in the wire at the diameter of the wire. So what do we want? We want a normal stress. And what do we already know? We know length increases by 1%. That is essentially the relative change in length, which is strain. We know strain. We also know the so-called material property, Young's modulus or elastic modulus, which means we can use Hooke's law. The normal stress sigma would be equal to E elastic modulus times epsilon engineering strain. And what is E? We said 4 gigapascal. We put it here. What is strain? We said it is increases by 1%. The relative increase or relative deformation is 1%. And we can use this because we are well within elastic limit. So 4 gigapascal times 1%, it is 0.04 gigapascal or 40 megapascal. Okay, so once we know the stress, we already know the tensile force of 4 Newton. So the area would be force over stress, engineering stress, normal stress. Or we can say stress is force over area. Of course, area would be force over stress. And the force is 4 Newton. The stress we said is 40 megapascal or 0.04 gigapascal. Giga is 10 to the power of 9. And then 4 over 0.04, that is 100 times 10 to the minus 9. We got 10 to the minus 7 meter square. Okay, which is, if you are going to say it, it will be 0.1 millimeter square. 0.1 millimeter square. So the diameter of the wire, of course, it is area would be area over pi. You take square root and you plug the number in, and this is what you're going to have. Thank you. Homework 2.2. We have a 4 millimeter diameter metal wire, EF 4 millimeter diameter wire. We know the modulus is 200 gigapascal. The Young's modulus, or the so-called elastic modulus, is 200 gigapascal. And the initial length before tension is 5 meter. From E to F is 5 meter. Okay, so we have the geometry is 3 meter from F to D, 4 meter from E to D. Okay, 3, 4, 5. If the maximum stress in the wire, should not be higher than 250 megapascal. Okay, within the EFL, the maximum stress should not be too higher than 250 megapascal. Otherwise, the wire may break. And the elongation of the wire, the elongation or the so-called relative deformation tension should not be longer than 5 millimeter. We want you to calculate the maximum load P P is here, pulling, the maximum load P that can be applied. As you can imagine, when you apply horizontal force P in the midpoint, the wire will get stressed. As a result, there will be tensile stress within the wire, and we want the stress not to be higher than 250 megapascal. At the same time, as you can imagine, when you pull it, the wire will get longer, and we want the elongation. The absolute change in length should not be longer than 5 millimeter. Okay, so these are the two constraints, and we want to know the maximum unload P force that can be applied. Okay, so to do this, we can first understand the relationship between the applied external force P and the resulting internal force within EF. So to do that, you can consider the balance of moment, around for DE bar, Okay, if we use D as our D point and the axis, so P times 2 meter, P times 2 meter will be a moment that's trying to rotate the DE bar clockwise. P times 2 meter would be the moment that's trying to rotate the bar clockwise. Meanwhile, the resulting tensile force in EF, we call it FEF. FEF, that is the force that's trying to counteract the P, trying to rotate the DE bar counterclockwise. So FEF times 4 meter. 4 meter is this length, and it should time the sine for this angle from EF to D. And what is that sine? And you can know that sine would just be 3/5. So that is our moment that's trying to rotate the bar counterclockwise. As a result, you would get the relationship between P and FEF. Again, P is your external applied force, horizontal force, at halfway between E and D, and FEF would be the resulting force in the wire. Okay, so we would have this relationship. P would be equal to 1.2 of FEF. Then let's consider the maximum stress. We set the maximum stress within the EF wire. Maximum stress, what's the definition? Normal stress would be force over area. FEF would be the tensile force or internal force within the wire, and the AEF would be the cross-section, normal cross-section area for the wire. We said this ratio, this stress, this force over area should be smaller than, remember, 250 megapascal. 250 megapascal. So as a result, we would have P equals to 1.2 of FEF, and FEF we said should be equal to or smaller than AEF times 250 megapascal. 250 AEF would be pi r square, and what is our radius? We said 4 millimeter diameter, so radius would be 2 millimeter. Our millimeter is 10 to the power of -3 meter square, and then don't forget megapascal is 10 to the power of 6 of pascal. Okay, pascal times meter square, that gives us Newton. Plug the number in, you would have the number as 3768 Newton if you are considering the stress criteria. If you are considering stress should not be higher than 250 megapascal within the EF wire, the P, the horizontal P, should be smaller than 3768 Newton. On the other hand, there's another condition. it has to satisfy. Now we have to consider maximum elongation. Here is absolute elongation. Delta for absolute elongation, EF for EF file would be, if we go back to our equation, would be FL over AE. Or you can say the absolute elongation is strain times initial length. And what is strain? Strain would be stress over area. And what is stress? Would be stress over elastic modulus. And what is stress? Force over area. Give us stress divided by E gives a strain times L give us the absolute change in length. So this whole thing times together has to be smaller than 0.005 meter, which is 5 millimeter or 0.005 meter. As a result, the FP would be equals to 1.2 of FEF, and it has to be smaller than, when you plug the number in 1.2, you keep FEF has to be smaller than 0.005 divided by this LEF 5 meter times A times E, and E is 200 gigapascal, 10 to the power of 9 pascal, and A would be, as we said before, 3.14, which is pi times R square. R is 4 millimeter divided by 2, which is 2 millimeter. And you plug the number in, you would have, when you consider the elongation, the P should be smaller than 3014 Newton. Okay, so when you consider both of these, then the overall, the horizontal force P, the maximum load, should be smaller than the smaller one between these two. Okay, so this is our problem. We want to know the maximum P when we have two constraints. One is for the stress level within the material. The other one is about the total elongation. And when we use the stress level, we assume it is within the elastic limit. Similarly, when we use the absolute elongation, we also assume it is within the elastic limit. Okay, thank you. Problem 2.3. We have a truss. The members CD and BC, they are made of the same material with the same or common E for elastic modulus or Young's modulus of 29 times 10 to the power of 6 psi, pound per square inch. And their cross-section area are for CD 0.75 inch square and for BC 0.6 inch square, respectively. 0.75 for CD and 0.6 inch square for BC. So for the applied forces shown, 25 kips, 25,000 pound of force to the left at D, 50 kips, 50,000 pound of force horizontally at E. For these two applied forces shown, we want you to determine the elongation of rod CD and rod BC, the absolute change in length for CD and for BC. Again, this is not statics, because in statics you would consider these to be rigid body and the elongation would be 0. But in this class they are not 0. And we have Hooke's law that they expand linearly when the stress level is low with respect to stress. Okay, so let's first consider for the CD rod. Let's consider the balance of forces at point D. Balance of forces at point D. We will draw the free body diagram at point D. 25 kips. Okay, 25 kips to the left Yes. And then for D, in order for it to be balanced, there will be two additional forces. One is for the pin D, one is exerted by the CD rod, okay? We call it FCD. The other one is by this DE rod, vertical DE rod. We call it FDE. And which direction are these forces for FCD and FDE? Well, you have to consider each of these bars are so-called two-force bodies. You can treat as one force at one end, the other force at the other end. So as a result of this structure, so the interaction forces at these two ends are always along the longitudinal axis, which means the force CD onto the pin must go along the CD bar direction. If this is 5 foot, this is 5 foot, 90 degree, then this is 45 degree going along this lower right hand side. Similarly, for DE, it has to be vertical. The force exerted by the DE onto the pin D would be vertical. Okay, so for at D point, we have one force to the left, and to balance, we need the FCD to go to the right, the lower right hand side. And then because FCD is has a direction that's going down, the FDE must be going up. So this would be our balance of force of free body diagram for point D. Okay. Based on this, what do we know? We know the horizontal force is 25 KIPS. 25 KIPS. And because of the similar triangle in this force relationship between this triangle and the real geometry triangle, we would know FCD, this force exerted at D point by CD rod. FCD must be remember this is 5, so this must be 45 degree, and so this is would be, if this is 1, this is 1, this would be square root of 2. So 25 KIPS times square root of 2. That will give us the force, the net force of FCD, 35.4 KIPS. And that is also the internal force within it. Okay, and it will be tensile force because as you pull D along to the left, the CD would be stretched, so definitely it will be tensile force. As a result, what do we want? We want the elongation, the absolute change in length, which is delta CD. Delta for change in length for CD rod would be, remember our equation, the delta would be FL over AE, or you can write it as F over A gives us stress over E gives us the strain times the initial length, LCD, gives us the change in length, absolute change in length. So now let's plug the number in. FCD, we just from the above 35.4 KIPS, which means 10 to the power of 3 pound of force. And then what's in the denominator? ACD. We said the cross section for CD is 0.75, so 0.75 inch square. And what is E? We said both CD and BC have common elastic modulus, which is 29 to the power of 6 PSI, or pound force per square inch. Okay, and then what is LCD? We know this is DE is 5 foot, CE is also 5 foot, so CD must be 5 foot times square root of 2. So you plug the number in, you would get an answer in foot, or you can convert it into inches. Okay, that's for the first part for CD. For second part, for BC, let's now consider the balance of forces at point C. So FCD, That's the same force, but now it's exerted by CD rod to pin C, okay, and it's going along this rod direction. And similarly, FBC would be the force exerted by the BC rod to the pin C here, and FCE would be by the rod CE to the pin C, okay, and we know in CD that's a tensile stress, so it must be pulling C upper left, okay, and as a result the FCE must be pushing the C towards the right, and because FCD is pulling up, the FBC must be going down. Again, we have to remember all these bars are so-called the two-force body, which means the net force at the end are going along the longitudinal axis for each of these bars. Okay, so this is what we have for the balance of force at C point. And from previously, we already know FCD. So now we want FBC. Remember, same as before, this triangle, the balance force triangle is same as the similar triangle, is similar to the triangle in the real geometry, okay, which means this is 45 degree, this is 45 degree. What that means is FBC, the one vertical relationship to the FCD must be 1 over square root of 2, or FBC. FBC would be FCD, this force divided by square root of 2. And if we plug in the number from previously, we would get FBC of also 25 kIPS, 25,000 pound of force. Then what do we want? In this case for BC, we also want the elongation. Delta BC, delta for absolute change in length. For BC rod would be force over area over elastic modulus times the initial length. Okay, and the FBC we already know. The area for BC rod cross-section area we said is 0.6 inch square, and the elastic modulus we said is 29 times 10 to the power 6 pound force per square inch, or PSI, and times LBC. LBC, based on the plot geometry, it is 5 feet. So you plug the number in, you would get the answer in foot, or if you converted that, you can have that in inches. Okay? Now let's look at the homework 2.4. It's a so-called statically indeterminate problem. So we said a centric load P of 400 kilonewton, downward is applied to a composite block, okay, a 3-part, shown through rigid end plates. One rigid end plate at the top, one rigid end plate at the bottom. The composite is sandwiched in between these two rigid plates, okay. In particular, the center iron plate. The center iron plate is sandwiched between two copper plates, one on the left, one on the right. The iron plate has elastic modulus of 200 gigapascal. The copper plates have the modulus of 80 gigapascal. And the center iron plate, let's assume they are rectangular in shape and they are 40 millimeters thick, while the outer copper plates are 20 millimeters thick. And all plates are 500 millimeters long, 500 millimeters long. Of course, this is not drawn to scale because this is 40, this is 500. It's not drawn to scale. And the other dimension is 100 millimeter wide, which means going into the paper is 100 millimeter wide. Again, the plot is not drawn to scale. We want you to calculate the normal stress normal stress along this vertical direction in the center iron core and the outer copper plates. Okay, we want you to calculate the normal stress along this vertical or axial direction, both within the iron core and in the outer copper plates, one on the left and one on the right. Again, we assume each of these blocks are rectangular and they have 20, 40, 20 millimeter in width, and the other dimension going into the paper is 100 millimeter wide, and the total length is 500 millimeter along the axial direction. Of course, it is not drawn to scale. So what do we want? We want the stress. So we first need to know the stress is defined as force over area. So we need to know the force because we already know the cross-section area, right? From statics point of view, let's assume the force can be separated into the force shouldered or borne by the iron part and the force totally borne by the copper part. Okay, let's assume the force by shouldered or borne by the iron part is FFE, while the combined force, vertical combined force shouldered or handled or borne by the copper is FCU, CU for copper, FCU. And from statics point of view, the force in the iron and the force in internal force in the copper combined should be equal to the external applied vertical force, which is P, which is 400 kilonewton. Okay, but based on statics alone, that's the only equation that we have. We don't have balance of moment because it's axial and there's no tendency to rotate. So one equation, two variable. That's why we call it so-called statically indeterminate problem, which means from statics alone, we cannot know FFE or FCU. And as a result, we also cannot know the so-called normal stress in either the center iron or the outside copper. But this doesn't mean it cannot be solved. When we start to consider deformation or shape change and then the geometry, we should be able to solve this problem. So from deformation point of view, we said, oh, the top and the bottom are so-called rigid end plates. Rigid end plates. Okay, which means to translate, it means the iron and the copper, they would expand or shrink in the same way. The absolute change in length for the iron in the center and the absolute change in length for the copper pieces on the left and right should be the same. Put it another way, delta Fe, delta for change in length within the center iron bar would be, based on what we learned in statics, assuming everything is within elastic limit, would be F over A, that is stress. Stress over elastic modulus, that would be strain. Strain times LFE, the initial length, would be the total absolute change in length. Absolute change in length for the center iron piece must be the same as the absolute change in length in the copper piece, which is FCU, force, internal force, axial force within copper divided by normal cross-section area for copper divided by elastic modulus for copper. So this is one more relationship that we can get after we consider deformation. Same deformation, and after we consider assuming the deformation is well within elastic limit where Hooke's law can be applied. That's one. The other one is from geometry point of view. You would know in this case the total cross-section area for the iron, which is 40 millimeter times 100 millimeter in the other direction, would be the same as the total area for the copper, which is 20 millimeter plus 20 millimeter, also 40 millimeter times 100. So the area for iron and copper are the same for the normal cross-section area. And the initial lengths, LFE, initial lengths for the iron piece and the copper piece are also the same, which is we said 500 millimeter. As a result, the LFE, LCU cancel out, AFE and ACU cancel out. We would have FFE divided by E, which is 200 gigapascal, equals to FFCU over 80 gigapascal. Gigapascal cancel out, which is just the FFE divided by 200 equals FCU divided by 80. Or put another way, FFE, the internal normal force along the vertical axis would be 200 over 80, which is 2.5 times FCU, internal force within copper. Okay, so now we have how many equations left? One is from statics, the balance force. One is from the consideration of deformation and geometry. Two equations, how many unknown? FCU, FE, FCU, two unknowns. And when you plug in the number, we can solve for the FFE is 286 kilonewton, while the FCU, the total force shouldered or borne by the copper pieces are 114 kilonewton. Again, I'm counting the total force for both pieces. So if you want to say the force within one piece, that should be half, which is 57 kilonewton. But here I just use the total. So as a result, the normal stress, again, the normal stress would be the normal internal force divided by the normal cross-section area. For iron would be 286 times 10 to the power 3 Newton. And the area for the iron would be 40 millimeter, which is 0.04 meter times the other direction. The cross section must be, your inches must be perpendicular to this line. So it's not 40 millimeter times 500 millimeter. It is 40 millimeter times the other dimension, which is 100 millimeter wide or 0.1 meter. And then you will get the internal normal stress within Fe. Similarly, sigma Cu for internal normal stress along vertical axis in the copper part would be the force 114 kilonewton divided by area, which is total 20 plus 20 a millimeter times 100 millimeter, or I put it here. And as a result, you would also be able to get the normal stress in the vertical direction in the outer copper pieces. Again, that is average normal stress in the vertical direction. Okay. Homework 2.5. This is another so-called statically indeterminate problem. Statically indeterminate problem, which is by statics alone you cannot solve it, but with consideration of geometry or deformation it can be solved. So we said a rigid bar EH from E to H, a rigid bar is supported by two steel wires of 1/16 inch in diameter. And we know the wires have elastic modulus E, or Young's modulus, of 29 times 10 to the power of 6 psi, pound per square inch. So we know the elastic modulus, we know the diameter for these wires at F and G, and we know this bar is rigid. And then it has a pin connection on the right at H point, pin and bracket at H. And knowing the wires were initially tied, okay, we want to know when you apply an additional 200 pound force, 200 pound force load P is applied at the end of E point. At the end of E point, we want to know the additional tensile force, additional tensions in each of the two wires, one wire at F, one wire at G. The additional tensile force caused as you press down with 200 pound force at E. That's one. The other one is we want to know the corresponding deflection, downward displacement, deflection. When you push down, the wires get slightly longer, the E would move down a little bit. The additional deflection at point E, assuming it's well within elastic limit. Assuming everything is well within elastic limit. So this is our problem. You have the bar, rigid bar, originally horizontal, hung by two metal wires, and we know the geometry, okay? And then we said you apply 200 pound of force vertically down at E. We want to know the additional tensile force resulted in each of these two wires. And also we want to know how much vertical deflection or downward movement the E point would experience, okay? And we know it's well within elastic limit. So to solve it, let's imagine what happened. Initially, this is our rod, and after you press down, it rotates a little bit. It rotates a little bit, and that's what we draw here. From H, it's fixed, but from G to G prime, from F to F prime, and from E to E prime. Okay, that's the deflection. So the first part is to consider statics. Consider statics, a balance of moment around H, the pin. Let's consider the balance of moment around H. Okay, so we have 200 pound of force at the E end, and the distance from this 200 pound of force to our axis, our H, is 10 plus 10 plus 10, 30 inches. Okay, and that is trying to rotate this EH bar which way? Counterclockwise. Okay, and let's, for simplicity, assume the resulting additional tensile force within F and G are both going upward, and the moment from F would be RF times the distance, which is 10 plus 10, 20 inches, and it's trying to rotate the pin clockwise, plus RG, the resulting additional tensile force in G times the distance, 10 inches. So this is our balance of moment from a statics point of view. We have one equation, two unknowns, RF and RG, and we cannot solve it directly. Here we didn't draw the free body diagram. If you do so, then you have to also consider the force at H. You introduce one more additional force at H, but then you have one more equation. That doesn't help you. So from statics point of view, we have one equation about the balance of moment, and we have two variables. And that's why we mean the problem is a so-called statically indeterminate problem, which means by statics alone, we cannot know RF and RG. On the other hand, if we simplify this equation, we would have the 10 cancel, 600 pound to the right, and the 2 RF and plus RG. That's from simplification. We would have the above equation. Okay, still one equation, two variables. Then to solve statically indeterminate problem, we have to consider geometric relationship. We have to consider so-called the strain or deformation. So I write something like this: delta F equals to 2 times delta G. So you see this delta F means the deflection for F point from F to F prime, and the delta G is from G to G prime. And because of similar triangle, we have 10 inch here, 10 inch here, which means from H to F is 20 inches. So from the similar triangle relationship, you can easily get delta G over delta F is 10 over 20, which is half. Or delta F would be double of delta G. Delta F would be double of delta G. Okay, because of the geometric relationship. We are using similar triangle. Okay, because of this, now let's think what is delta F and delta G. From earlier what we learned in this class, delta F would be force RF over area, cross-section area for the F wire that gives us stress, stress over elastic modulus for the wire that gives us the strain, strain times LF, that is the initial length. LF, that's the initial length, would be equal to 2 times delta G. What is delta G? Similar, RG over A over E times the initial length, LG. Okay? And we know the two wires, for F wire and G wire, they have the same cross-section area because they have the same diameter, 1 over 16 inches. And then they are made of the same material, both 29 times 10 to the power of 6 psi. So AE term and AE term are cancelled. We would have RF times LF. What is LF? Initial length of F would be, you can see 8 plus 10, 18 equals to 2 times LG. What is LG? You find it is 10 inches. So 18 times RF would be 2 times LG. And if we simplify, uh, divided both sides by 2, that will be 9, that will be 10, and then it will be RG equals 0.9 RF. That is simplification from this equation. Okay, so then we have one equation, two equations. Okay, we have two variables. One is RF here. We have another variable RG. Two linear equations, two variable. We can solve it, and on the other hand, we can just simplify because RG equals to 0.9 RF. RG equals 0.9 RF. We would have 2.9 RF equals 600 pound of force, and then you can get RF as well as RG. RF as well as RG. Okay, I omitted them here for your own benefit. Then we would solve the first part of this equation, the additional tensile forces in each wire. RF is the additional tensile force in F wire, and RG would be the additional tensile force in G wire. And then about deflection at E. Deflection at E, from geometry, you can easily find that delta E would be 3 times of delta G. 3 times of delta G. And what is delta G? It would be RG over AE times LG. The internal force divided by normal cross-section area for G. That gives you the stress within G divided by the modulus within the G material, that gives us the strain based on Hooke's law, and strain times the initial length of the LG wire, that gives us the total deflection. And you plug the number in. G is 186 pound force. A is pi r square, pi over diameter 0.0625 inch divided by 2 square times elastic modulus 29 times 10 to the power of 6 pound per square inch, and times LG. What is LG? We said from here to here is 10 inches, so times 10 inches, and in the end we would have the answer. Okay, homework 2.6. So for this problem, we have a tensile force of 2000 Newton applied along the longitudinal, the long axis, to a test steel sample with rectangular cross-section. Rectangular cross-section. We know the steel material has property of E, elastic modulus of 200 gigapascal, mu for Poisson ratio of 0.3. So when this force is applied along the longitudinal axis to this steel test sample, what about its dimension? We know its initial length is 100 millimeter. Initial length is 100 millimeter. It has a rectangle cross section with thickness of 2 millimeter and the width of 10 millimeter. From here to here, the width of 10 millimeter. It's tensile force. Okay, we want to calculate the absolute change in sample length in this direction, sample thickness in the y direction, and the sample width in the z direction. And we also want to know the change in sample cross-section area, the absolute change in sample cross-section area. Okay, so to do that, let's first apply what we learned. What do we know? We know the force, we know the material property, and we know the cross-section area. At least we can get the so-called normal stress, and with the Hooke's law within elastic limit, we can get the normal strain. Epsilon x means epsilon for strain, the relative deformation. X subscript x means along the x-axis or the longitudinal axis. Epsilon x, based on Hooke's law, would be sigma x, normal stress along x direction, divided by E. We are assuming the material is isotropic. It has the same elastic modulus for different direction. Okay, and what is sigma x? It would be the F, the axial tensile force divided by the normal cross-section area. The cross-section area that is perpendicular to x-axis. Okay, what is our force? We said is 2000 Newton. What is our area? As you can see, it would be 2 millimeter times the width 10 millimeter. The thickness 2 millimeter times the width 10 millimeter. Okay, or 2 millimeter is 0.002 meter. 10 millimeter would be 0.01 meter. That is our area, force over area. That gives us the normal stress along this x or horizontal longitudinal axis, and stress over strain, stress over elastic modulus, which is 200 gigapascal, 200 times 10 to the power of 9 Pascal. This we would have the strain. If you plug the number in, we would have the epsilon x, the strain along the x-axis, the longitudinal axis, would be 5 times 10 to the minus 4, a very small number. Okay, now we have the strain along the longitudinal axis. What do we want? We want the absolute change in length for sample length. Okay, so the absolute change in sample length, data x, data for absolute change in length, based on definition of strain, would be strain along x-axis times Lx0. Lx, initial length 0 for initial. Okay, so you plug the number in. From above, we have the strain would be 5 times 10 to the minus 4 times initial length, 100 millimeter or 0.1 meter, and you get the number. On the other hand, for B, the absolute change in sample thickness, the absolute change in sample thickness, well, in the y direction, we have to remember for isotropic material, that's a Poisson ratio that relates the strain in one direction to the strain in the direction that is perpendicular to it. In this case, delta y, the absolute change in y direction in the vertical direction would be strain epsilon y in the y direction times the initial length. And what is epsilon y? Well, if you remember the broader Hooke's law, that relates epsilon y would be Poisson ratio times epsilon x, don't forget the minus sign. Or you can say the Poisson ratio is defined. Eta is defined, mu is defined as epsilon y over epsilon x with the minus sign. So epsilon y would be mu times epsilon x with the minus sign in front. And of course, you still write the initial length along y direction, or Ly0. So epsilon, the Poisson ratio mu is 0.3, minus sign we put it in front, and epsilon x is 5 times 10 to the minus 4, and then Ly, the initial length in the vertical y direction, is 2 millimeter thick, which is 0.002 meter, and you would get the number. Similarly, for C, the change in sample width, along the y direction, delta z, delta again is for absolute change in sample length. Subscript z means along z direction would be epsilon z times Lz0. The strain along z direction times Lz0, the initial length along Lz direction. Okay, and similarly, as before, the strain along z direction would be Poisson ratio times strain along x direction with a minus sign in front. Again, remember, the Poisson ratio is defined as epsilon z over epsilon x with a minus sign. So epsilon z would be epsilon x times mu with a minus sign, and Lz0. So plug the number in 0.3 with a minus sign in front times epsilon x, 5 times 10 to the minus 4 times initial length in z direction, which is 10 millimeter, and then you can get the other number. Okay. Finally, for the absolute change in sample normal cross-section area, the cross-section area that is perpendicular to the longitudinal axis or to x-axis, the delta A, I would write as the final cross-section area minus initial cross-section area. Initial cross-section area would just be dimension along y direction times dimension along z direction, 0 for initial, and then the final state would be initial dimension along y direction times delta, the absolute change, times the initial dimension along z direction plus the delta along z direction, and then Ly0, Lz0 times, and the last term got cancelled. Delta term, these are second order term which is very small, got neglected. So it would approximately would be delta y times Lz0 plus delta z times Ly0. So from previous, you know the delta y, you know delta z, you know Ly0, Ly0, you plug the number in, okay, and you would get the absolute change in sample normal cross-section area due to the tensile force, and it's going to be a very small number, okay. Finally, for homework 2.7, two blocks of rubber, as illustrated these gray regions with shear modulus G equals to 10 megapascal are symmetrically bonded to rigid supports. This light blue are rigid supports, and the center plate, rigid center plate A, B. This copper colored center plate. So we have two pieces of rubber, one on the left, one on the right, on each side of this AB plate. And the rubber are bonded between AB plate and the rigid support. The blue ones are rigid support. So we have some dimension information, C, which is, if you see the width from here to here, C dimension is 100 millimeter. And we also know the load P applied is 50 kilonewton. 50 kilonewton. We want to calculate the minimum value for dimension A, which is, you can view it as thickness for the rubber blocks, and the B, which you can call it the length of the rubber block. So B is along the x-axis, if we say. A is along y-axis, and C is on z-axis. Okay? So that is the situation. We want to calculate the minimum dimension for A, thickness of the rubber blocks, B, length of the rubber blocks if the shearing stress within the rubber block should not exceed 1 megapascal, and the deflection of the plate. So as you push A, the A plate will move along this direction, and deflection of the plate is at least 4 millimeter. At least 4 millimeter. So we want to know the AB dimension if this is what we want. If the stress level should not go higher than 1 megapascal, while the displacement must be 4 millimeter or longer. Okay, so this is our problem. And from the description of the problem, first thing you notice is the shearing force at each of the interface. On the left interface, the right interface of the AB block would be half of P, because the P is trying to push AB to the along positive X. So the shearing force, one on the left, one on the right, is counteracting it, and each of it would be half of P. Okay, and then the shearing stress, we said it should be 10 megapascal or smaller. 10 megapascal or smaller. Okay, this is our tau. Shearing stress is defined as shearing force over area, and the shearing force is half of P, and the cross-section area of interest would be, as you see, B length times C width, and B we don't know, C we know. From here is 100 millimeter or 0.1 meter, and the P we know from here is 50 kilonewton. Half P is 25,000 newton, and this ratio has to be smaller than what we said, 10 megapascal, 10 times 10 to the power of 6 pascal. As a result, we would be able to solve for B. B would be greater than 25,000 newton divided by the stress 10 to the power of 10 times 10 to the power of 6 times 0.1 meter, and we would get the result. Okay. Similar, once we have the B, now let's consider the other constraint on the displacement constraint. From geometric relationship, we have the rubber block of thickness A and the displacement of delta. If we view it from the top, again, this is an exaggeration of delta. If you view it from the top, it's more likely to be something like this. A is along what we hear, y-axis, and the delta is the displacement along B is actually along x-axis. And this changing angle, we call it essentially strain. And when the angle is very small, the angle is the same as tangent of that angle, and the tangent is defined as delta in this case over A. Tangent is delta over A. So gamma, this gamma is approximately tangent gamma in the approximately delta over A. Again, delta is our displacement or deflection for the center AB plate, okay, over A. At the same time, based on Hooke's law, we would have the strain would be shearing stress over shear modulus. Hooke's law gives shearing stress would be shearing strain times shear modulus. So shearing strain would be shearing stress over shear modulus. And what is shearing stress? We said before it's Fs over A or Fs over BC divided by G. This is another relationship for shearing strain, and these two should equal to each other. So what we have is delta over A, displacement or deflection over A dimension, the thickness, would be equals to Fs shearing stress for each of the interface over BC times G. And from this relationship, we can easily get the dimension thickness A would be delta times BCG divided by Fs. Okay, and Fs from previously we know is half of P, so A should be equal to delta BCG over half P. And for delta from previous, we know it should be at least 4 millimeters, so delta should be greater than 4 times 10 to the minus 3 meter. And the B is what we got. It should be greater than this value, whatever it is. And the C is what we have given, 0.1 meter or 100 millimeter. And G is the shear modulus, 10 times 10 to the power of 6 Newton per meter square divided by shearing force. And by plugging the number, you should be able to get the result.